Good evening, everyone, and a welcome to the inaugural session of the webinar and Fireside chat organized by TCS Research in collaboration with ACM India. I'm Rajiv Shori, the CEO of the University of Queensland, IIT Delhi Academy of Research, and member of the ACM India Council. And it's a great pleasure to be here this evening. TCS Research is a platinum tier institutional partner of ACM India. On behalf of ACM India, we are pleased to launch this joint initiative between our two organizations. Here's a session where we bring together some eminent experts for a conversation over a particular technology topic. Conversation, perhaps a debate among themselves, and question and answers with the audience. The session includes representatives from academia and industry, and it surely promises to be a lively one.
My name is Lavkesh. I'm a principal scientist at TCS Research, and I will be moderating today's session around explainable AI. And this is the first in a series of webinars jointly organized by ACM India and TCS Research. And as you know, TCS Research celebrated its 40th anniversary this year. And over the past 40 years, TCS has been consistently investing in foundational research in computing and its intersections with the physical, biological, behavioral, and mathematical sciences. The resulting inventions have brought competitive differentiation to our stakeholders in industry and sustainable solutions for social welfare. So any researchers out there looking for positions in these areas, please reach out to us over email or social media. Coming to today's proceedings, the first event is the presentation by Professor Ashwin Srinivasan, followed by a brief Q&A. Following the talk, we will have an informal fireside chat with Tanuja Ganu, Indrajit Bhattacharya, Shrikanta Bedathur. It's my pleasure to introduce the area of reasoning and inductive logic programming, Professor Ashwin Srinivasan. Ashwin received his PhD from the University of New South Wales.
As Lavkesh said, I finished my PhD in 1991 in the University of New South Wales. Coincidentally, I'm back in New South Wales just at the moment, so it's 11:30 at night for me. So if I'm slightly incoherent in this talk, you'd forgive me for the fact that it's not just late, but I've also just gotten off the plane. So I'm sort of handicapped in at least two ways, possibly more. Nevertheless, my day job, I'm at the computer science department at BITS Goa. I also head the Artificial Intelligence Center for AI across BITS. It's called AppCare. You can look us up on the web by just searching for AppCare at BITS. But thank you also to the ACM and to TCS Research for inviting me to give this talk. It's an unusual talk for me. I normally try to avoid giving position talks, and this is one of them. I'll try to back it up with some results, but nevertheless, I should say that this is not a normal kind of talk for me. The title of the talk is Two Understandability Axioms for Machine Learning with Humans in the Loop. You should get some warning from the fact that I've chosen to call these axioms, and thereby washing my hands of any responsibility if the axioms are not true. So the talk itself is inspired by work by John McCarthy. Specifically, the first axiom that I present owes directly to something that John McCarthy had said many years ago, possibly in the late 70s, and to Donald Mickey, to whom I owe a debt of intellectual and gratitude, and to whom the content of Axiom 2 can be traced to perhaps the 1980s. I have to give you a warning that this talk will anthropomorphize machines. So it sort of takes the position that machines are people too, as such, and you'll see what I mean in a moment. So the context is the following. The context is a straightforward context that we have come across many times in machine learning, that as people, we are not able to deal with the scale and diversity of data as we have it now. But we do have programs that are able to handle the data, but construct models that we do not understand, which leaves us with two options. Either we do not need to understand what these models are, or we do need to understand what these models are. So my interest has been for the longest time, ever since my PhD, so in 1991, is in the case when option one, which is that we do not need to understand, is not an option as such. So, and there are many cases where this comes up in science. For example, if we're constructing models by machines for natural phenomena to try and understand how things are, then we do need to understand how things are. So it's not good enough to just have models that can predict very accurately, but we also need to understand how these models are predicting what they're predicting. In engineering, models constructed by machines for monitored phenomena like, processes, plants, that sort of thing, which to help us identify faults, how systems work, or assist with new design, are cases where we do need to understand the models constructed by machine. Models constructed in business, which are being used increasingly to model us as people. So a very simplistic sort of recommender systems are an example, of course, but in general, models will be constructed which of increasing sophistication, which will be used to model who we are and what our interests are and what we like and what we dislike, and to exploit that either for profit or for more complex reasons. These sort of cases are examples of using machine learning where humans are always in the loop. The models are being constructed for us, and it is important that they are constructed, I think, in a particular way. So an example of a human in the loop model, which I've been involved with for a substantial amount of time, is one which involves a biologist who gets observational data from some biological system, and those are converted to some data in an understandable way to a modeling system. The biologist also provides what I will call domain knowledge, which will be, I believe, the subject of the subsequent discussion, although not necessarily the same way that I intend to use it, but nevertheless. The modeling system constructs models and explanations, which are then looked at by the biologist, who then may conduct some further experiments, may modify the data, may modify the domain knowledge, or provide some extra constraints, which will modify the models constructed by the system, which will then return new models, new explanations, and so life goes on. So this is an example of the kind of use of machine learning that I've been both interested in and been involved with for some length of time. So machine learning with humans in the loop has some requirements, and we need to have machines. We need to be able to tell machines what we know. So, for example, this arrow from the biologist to the domain knowledge is an example of that. So we need to be able to tell machines what we know, but can the machine make sense of it? And here's an example of the kind of treating machines as people, in the sense that we're talking about a machine understanding what we tell it. And I'll come to what it means for a machine to understand what we tell it in a moment. But we would like machines to be able to at least make some useful make some use of the information that we provide it with. The machines will also have to tell us what they know, which is the second leg of this this loop before in the slide before, which comes up with models and explanations. But can we make sense of it? And these are two requirements that we would need machines to make sense of the information that we provide them, and that we should be able to make sense of what machines tell us, which I think are quite important requirements for building machine learning systems with humans in the loop. It does not mean, of course, that machines have to represent internally or process information like us. This is a requirement of understandability, or requiring the inputs and outputs to be understandable in some way. How we process the information and how the machine processes the information is not really the subject of what I'm talking about. So before I start, I should clarify what I mean by a system that builds models, or a machine that learns. So minimally, I will assume that it's a box which basically takes in data, has some loss function. It has some notion of structure of a model, some notion of parameters of a model, and it produces predictions and some explanations. So this is the kind of box that we're talking about. And when we consider this kind of box, let's take the first part, which is us telling machines what we know. So, and now there are several ways in which we can tell machines what we know. In this slide, which looks more complicated than it really is, basically we have what I've called domain knowledge. I've indicated here by the letter B, or background knowledge. The box T is some kind of transducer or transformation program that allows you to convert, say, the background knowledge into some form of data which the learner can understand, or you can use the background knowledge to. It's not. I don't mean the same sort of background knowledge is used in all of these cases, but basically the point is that background knowledge can be used in many places to either to provide information about the structure, about the parameters, about the loss function, and even to modify the data. Now, in my talk today, I will be only providing examples of changing the data as such using background knowledge. But that's not the only way to do this thing, as many of you would already know. The first of the two axioms that I wanted to propose was what I call the machine understandability axiom, which reads like this: that if providing domain knowledge improves a machine's predictive performance, then the domain knowledge is machine understandable. Now, you can, as I say, contest this, and axioms are contestable. But nevertheless, let's go with assuming that what happens if this were true as such. So it is a sufficiency criterion. It's just saying that if the machine's predictive performance improves, then the domain knowledge is understandable. It does not say that if what happens if the predictive performance doesn't improve. Does it mean that the domain knowledge was not understood by the machine, or or something else. Nothing is said about that. It's just saying that if things improve, then it was understandable. Let me give you an idea of what I mean. So here is some data of, say, a classification problem with pluses and minuses, and a machine is asked to make sense of this data. Now, of course, there are several ways of you would go about it, and you could possibly as it stands in just this two-dimensional world. It seems a bit difficult because the pluses and minuses are so close to each other that the model would seem to be an exceedingly complicated model to try and separate out the pluses from the minuses. So you could do something else. You could maybe transform it to a different space and then see whether the minuses move away from the pluses, and you could draw a simpler kind of separator. Something like that could be done. Or you could tell it what we know about this problem. Now, perhaps what this problem was about port cities in the world. And if you actually gave it information about the location of places and of a map of the world, and the machine suddenly realizes, hang on, what this is effectively the fact that all the pluses are actually ports, and all the minuses are things which are not ports, including places in the water or places deep inland and so on. So this is the kind of thing that I have in mind when I say that it's providing what we know helps the machine understand things better. So and essentially what I'm saying is that the domain or background knowledge allows us to make sense of the data in the sense that it should not look random to the machine. So it should not look incompressible to the machine. So as it stands in this thing, it sort of looks random, or believe me, it can be made to look as random as you want with this problem. But given the background knowledge of the world map, it doesn't look random anymore. There's some point to the pluses and some point to the minuses. So in some sense, the domain knowledge is allowed the machine to compress the information into a much simpler kind of statement about what the points are about. Now, it is somewhat easier for us, not so much necessarily for the most efficient thing to do, but nevertheless, it is somewhat easier for us to provide this background knowledge in a language, either formal or natural. I'm not saying that it has to be a formal language, but here's an example of the kind of background knowledge in a different problem, say in a biological problem, saying that perhaps for inhibiting this kind of protein that we're looking at, the presence of something like a peroxide bridge is relevant. The target site on the protein that we are looking at is at most 20 angstroms. So statements like these are fairly straightforward for us to come up with for a problem that we know something about. And it's somewhat easier to provide this kind of domain knowledge than it is to provide a more mathematical form of domain knowledge, which we can discuss later, perhaps. So here are some results from some work that I've done with a colleague of mine on using domain knowledge, providing domain knowledge to deep networks, for example. Two kinds of deep networks are illustrated here, graph neural networks and multi-layer perceptrons. And what you're supposed to make of this is the following, that there's a flat line at the bottom. These are 78 or 73, sorry, data sets concerned with toxicity in drug design. So each one of these dots is a full data set. There are about 250,000 chemicals here involved in this, but each data set is a particular toxicity problem. And the flat line is essentially the predictive accuracy that you get from using, say, a GNN or an MLP without any domain knowledge. What is this domain knowledge involved here? The domain knowledge involved here is various statements of general chemistry, like the encoding of what are benzene rings, what are alcohols, what are ketones, what are so sort of like the world map, but just for biology. And the zigzag line that you see are the predictive accuracies that you get from once that domain knowledge has been provided to a GNN or an MLP. Now, how has it been provided? Well, you'll have to read the paper for that, but it's a fairly straightforward conversion of the logical statements or the logical definitions of these chemical definitions, which then transform the data into a different form, and that transformed data is used by the GNN or the MLP. The important thing is that you get this tremendous jump as soon as you provide this information. Now, in principle, a GNN or an MLP can invent the concept of a benzene ring for itself. It can invent the concept of alcohols and all of those things, given enough time and effort. But when we know it, why not tell it? And it does make a difference, as you can see. The predictive accuracy is across the board. I mean, there's just a few guys where the predictive accuracy is pretty much unchanged. Few data sets. Almost all the other data sets, the accuracies gains, and they're quite high. The gains are anywhere from 10 to 30% in some cases. So it can make an important difference to the predictive accuracy. The second part of the talk, I want to focus then on the second leg of that machines in the loop. So I've shown you at least some instances where providing domain knowledge can make a big difference. According to my understandability axiom, this sort of providing this domain knowledge has improved the machine's predictive accuracy. So I would say that the machine has actually understood what we told it. And it's built some model with the GNN and with the MLP, but can we understand that model? Most of the explainability work in the literature focuses on the second part about listening to what machines have found. But I do think that this first part is an important part of the human in the loop story, which is often somewhat either assumed to have been solved or neglected altogether, but it can make an important difference. Humans can play an important role in assisting machines. But now let's look at the second part of this. So we do get this big predictive accuracy jump, but here then is the problem, which is sort of well understood so far, that here's the corresponding model that was constructed by the machine used to achieve this increased predictive accuracy. This is an example of the weights from the MLP used by the GNN. So based on the graph encodings constructed by the graph neural network to produce the final predictions. And although the predictions are greatly improved, what are we to make of this model? And now we had a way of characterizing what it meant for machines to understand what we said, and what are we to make of do we have a similar way of characterizing whether we understand what the machine has said? And there is this distinction, of course, which is made in the literature between black box and white box models, where black box models are examples are like deep neural networks, which have high predictive power, but the models are somewhat difficult to understand. And I put a question mark because it's not the case that the models are difficult to understand. The models are difficult to understand depending on who's doing the understanding. They're quite people well versed in the construction of deep neural networks can probably understand what's going on. So it's not the case that the models are inherently difficult to understand. Just depends on whom they're being built for. There's limited use of prior knowledge, apparently. At least there's no explicit way, say, as in a probabilistic setting or of the use of prior knowledge. And but it can work very well with low-level data. A corresponding distinction that is made is of, say, logic-based or symbolic models, where the predictive power may not be as high, but the models are somewhat easier to understand. Again, I put a question mark because I don't believe that, and I have many cases where I have seen this happen, where it is not the case that just because you adopt a symbolic representation that the model is easier to understand. But there is some way in which you can use prior knowledge, and they may not work very well with very low-level data. These things are definitely true of these kinds of models. So let's look at this model again. So you can do a kind of analysis of this prediction, I don't know, by doing some layer-wise relevance propagation or something like that, and it'll say something like, the inputs in the order of importance are these F7, F63, whatever, they're followed by F39, F62. These are the input features that are important. And then, but the difficulty arises, of course, that we don't have any idea what these Fs are. And even if we did have an idea, we may not know how they're combined in later layers of this multi-layer perceptron to create new features, and we have no idea what those new features really stand for as such. But they must be standing for something, because otherwise you wouldn't be getting this kind of predictive accuracy increase. So this brings me to my second axiom, which I propose in this talk, which I think which gives a way of assessing in a logical sort of manner what it means for a machine's explanation to be human understandable. So my claim is that if the machine's explanation is refutable, then the machine's explanation is human understandable. Refutable in the sense that you can say that I think that this explanation is either incorrect or incomplete, or just downright wrong, for example. Could be wrong for being incorrect or incomplete, but at least you have to be able to say that I think this explanation is wrong. Again, it's a sufficiency criterion. If it's not refutable, then I'm not claiming anything about it being understandable or not. All I'm saying is that if the machine's explanation is refutable, then it's understandable. Perhaps the contrapositive of this is more immediately obvious, but it's sort of strange to propose something in its contrapositive form. But the contrapositive can shed some light on what I'm talking about, which is that you cannot understand what you cannot. If you cannot understand it, then you cannot refute it. So if you can't understand something, then you can't say that that I think you're wrong. Of course, that doesn't stop people from doing it. I'm just saying that it's not a very reasonable thing to do. Now, there are, of course, machine learning programs that explain. There are Whitebox machine learning programs which produce both the prediction and the explanation. I've left out these loss function parameter structure arrows just for clarity here. Or there are sort of Greybox things which basically take Blackbox and bolt on a Whitebox. Doesn't necessarily have to be a kind of post-hoc bolt-on like some of the explanatory models tend to do. It can be something where the Whitebox talks to the Blackbox and constructs explanations while the Blackbox constructs the predictions. These are not the only options. I'm just giving you some idea of ways in which these things can be done with black boxes. An example I'll give you of a Greybox model, because the Whitebox model is obvious enough, is some work which we've done with TCS Research and some students at BITS, was to construct Greybox models for COVID-19, for example, where there were some black boxes which were extracting features from COVID low quality X-ray images, and we were trying to identify COVID patients. It was a kind of hierarchical model which basically extracted some kinds of features. Those those S features were symptom features, and then they were used by a higher level model which also had access to the image data. So these were extracting radiologist understandable features. So how did we know to build this S model and this R model? We asked the radiologist what sort of features did he or she, it happened to be a he in that case, thought were important to predict COVID, and then built extractors for that. These were standard sort of deep network models. And these features which were extracted, which are essentially sort of probabilistic features and their probabilities, were used to construct a symbolic model, like a decision tree, which then did the prediction. Now, the final tree model had, in fact, the same predictive accuracy of 98% as an end-to-end single black box MLP. This is not always the case. I mean, it can be the case that symbolic models can end up being worse, but in this particular case, we didn't find any great difference in the using an end-to-end single black box model or using this low-level feature extractors followed by a symbolic model. The features were sort of obviously domain-relevant features that were extracted by deep networks. And the explanations was sort of simplistic explanations of the decision path used by the tree to reach a particular conclusion. And now here's the interesting part of things. So the explanations were basically, there were these baseline features which were extracted by the deep networks, which are the thing with things on the right. There's descriptive textual features which said, the various kinds of features, their presence was, high or medium or low probability, and these were put together in some way by the induction engine, the decision tree, to decide whether a particular X-ray was COVID positive or negative, for example. And the description of the prediction is the standard sort of decision tree type explanation that you get from. But the interesting thing for us was the assessment of these explanations by these two boxes, the white box and the blue box, are two different radiologists. And the vertical column is the prediction, the radiologist's opinion about the prediction, and the horizontal rows are the radiologist's interpretation of the explanation being provided. So the prediction, so the radiologist thinks either the model's prediction is correct or incorrect or is unsure, and then says that the explanation, which is this decision tree type explanation, which is that the air space opacity is low and the cardiomechanism is probability is low and so on, and that's the reason for it being whatever COVID positive. So the radiologist then classifies these explanations as being sufficient, in other words, sufficiently good enough as an explanation for whatever it predicts, or insufficient or incorrect. You can see that when the radiologist thinks the model is correct, by and large, he thinks the explanation is sufficient. But when it's incorrect, he thinks it's incorrect. He thinks, that the model is insufficient or incorrect in some number of cases. Each radiologist, the radiologists, by and large, have different ways in which they categorize the explanations when when they think things are going wrong. But the important thing over here is not that the actual numbers themselves, but that we are able to put in some numbers at all. So the fact that a radiologist can actually say that this explanation is insufficient or incorrect or is sufficient is the interesting thing here. Not so much the number of times each one said it. So what's happened here? Okay, yeah. So here is an example. So by essentially what a radiologist is doing over here by saying that something is insufficient or incorrect is he both of the radiologists were male. I think it's a sort of common phenomenon amongst radiologists. He's essentially refuting the explanation produced by the machine to classify a particular image. So refutation, by refutation, it's not that I don't like it or I don't believe it, but you also have to categorize the error in the explanation and also provide reasons why that explanation is wrong. So here's an example of an explanation that was produced by the machine. It's a symbolic model, so this general understanding is that this is an explanatory model. The radiologist says that this explanation is incorrect because, in fact, you've done a wrong job of detecting airspace of pacification. And there's also something else that you've missed about some fixed hiatus hernia, and that the features that you picked up for deciding on COVID are not really that relevant to COVID as such. So this tells us several things. It also tells us, for example, that the feature extractor may be doing the wrong thing. Tells us that perhaps we missed some feature, which the radiologist has suddenly now decided that is important. And you can't say, well, you didn't tell me about that before. You just have to cop it on the chin and move on and say, okay, well, now he wants us to look at hernia or fixed hiatus hernias, and we have to sort of extract that now. And the whole point about doing this whole thing in a loop is that you have to sort of take what is given and then try to deal with that. So this is what I mean by a kind of refutation, which basically not just says that I don't like what you're saying. I should point out that so the fact that I should point out that the fact that he's able to say this sort of thing, minimally at least, suggests to me that he's understood why the machine is making this decision. And he's able to say, no, I think you're wrong. Now, I should point out that this use of the, by tying understandability to refutability gives two important, links up to two important aspects. One is it sort of makes there is obviously the kind of scientific aspect to it by tying hypotheses or explanations to refutation. So if something is to be scientifically sort of acceptable, it should be refutable in some way. So in that sense, this is a positive thing. The other thing, surprisingly, is that it also has some role in the whole legal business, because if you want trustable machines as such, you must be able to refute what they're saying. And although that seems to suggest that this axiom, although this is a sufficiency criterion, it may well be something stronger, maybe needed for trustworthy machine learning. You may need it as a necessary criterion, but at the moment, I'm just going with this as a sufficiency criterion. Coming back to this, so yes, so it's not the case that just because we have a symbolic model, I mean, this, although it was not the case that just because we had a symbolic model, our accuracies were low. The interesting thing here is it's not just the case that because it's a symbolic model, the explanations are adequate, or it's not the end of the story to say, well, we've produced this symbolic model, so that's it, we're done. No, we're not done, because now we produce a symbolic model, we produced it in a way that the human in the loop can understand it, and in fact, once the human understands why you're actually saying something as a machine, you better be prepared as the machine to be corrected as such. So, and that is, I think, an important part of this closed loop form of machine learning, which I've outlined in this slide, which is not, I mean, it's not rocket science what I'm saying over here, but it's still not many people, surprisingly, seem to be doing it like this. So here's a sort of operational human in the loop machine learning, operational form of all of this, which is you first identify the relevant data representation, in other words, possibly the features or the relations, and then build automatic extractors, which can be black box machine learning. And in fact, very effective extractors can be built with sort of modern, say, deep learning type techniques. And then you use a formal model construction that uses this data representation to construct models with as high a predictive performance as you can get with either a Whitebox or a Greybox machine learning approach. And then you show the explanations that you've found in terms of the data representation that were identified in the first step. And the fourth thing, which is the what I think, I mean, up to this point, people do this sort of thing routinely, although they won't possibly tell you that they're identifying relevant data representations. They'll say, we'll just find these relevant things ourselves. But I do think that providing relevant data representations does help, certainly with constructing refutable explanations. Now, the fourth step, though, is to provide tools for fixing data issues, for altering the representation and the extractors, and for revising the model based on the refutations of the explanations. So once you have some explanations that have been refuted, you now have data essentially on how to go about fixing either the representation or the model and so on. And that has to, of course, be automated or semi-automated, but some mechanism has to be there. Otherwise, doing this just in one shot end to end is not going to be sort of sufficiently good enough for machine in the loop, for human in the loop sort of machine learning. There are improvements for the axioms, which I won't go into. Obviously, I've focused on predictive accuracy. A better way would be to focus on expected loss. There are better versions of the human understandability axiom, which is, for example, being done by Stephen Muggleton's group in Imperial. For the approach they're taking is saying that if a machine's explanation increases the human's predictive performance, then the machine explanation is beneficial to the human. If the machine's explanation decreases the human's predictive performance. So just because once you've seen an explanation, you might do worse. I mean, radiologists are sufficiently confident people that they may disregard the machine, but it may not always happen that way. So this is about beneficial and harmful explanations. So there are changes and improvements to these axioms, but mine are sufficiently simple to be sort of characterized in a logical fashion. So my summary to close is essentially that I'm proposing that we should really be going from explanatory AI to understandable AI. So imagine, for example, learning machines that suggested to Kepler that an ellipse best fitted Tycho's observations of the orbit of Mars, or to Ramanujan that numbers had a particular pattern, or a biologist on how to modulate the immune response for autoimmune disease, or to you on what to read next based on some things that Gmail or whatever has worked out about you. All of these things, machines are talking to the people for this kind of collaborative exercise to be useful. Explanations have to be understandable. They have to be understandable by the machine, and they have to be understandable by the people. So we have to think about helping machines understand humans, and we'll have to think about helping humans understand machines. And that's where I'd like to stop. I'd thank my colleagues and friends and experts, Michael Bain, Ross King, Lavkesh, Gautam Shroff, Titraj Dash, the radiologists who were involved in the COVID work, some students who did some excellent work on the on that COVID problem, institutions like the SCRB, BITS, UNSW, and TCS Research. There's some papers and things which are relevant to what I spoke about. But I'll stop here. I think I have no idea if I'm over time or under time, but that's what I had to say.
Thanks, Ashwin. This was a great talk. We have time for maybe one or two questions, and then we have to move on to the fireside chat. All right, so I think what we'll do is we'll move straight to the fireside chat. So I'd like to introduce Indrajit Bhattacharya, who's a principal scientist at TCS. I'd like to introduce Tanuja Ganu from Microsoft Research. And I'd like to introduce Professor Shrikanta from IIT Delhi. Good. So I guess everyone's online. Hello. So I think I'll fire off the first question after Ashwin's talk. So as a response to some of the slides you presented, and also as a response to some of the work that's happening in machine learning at the moment with regards to explainable AI, the concern that I've always had was that it's a case of machine learning researchers developing techniques for XAI that are being consumed yet again by machine learning researchers or machine learning developers, basically the machine learning community. There is in this entire process of developing XAI techniques, there doesn't seem to be any involvement of the domain expert, like in the examples that you presented. just a little while ago. I mean, it seems to be an anomaly, really, the way you've devised your explanatory model, rather than the norm. And so my question is the XAI community really solving the right sort of problems when they're focusing on things like feature attribution and saliency maps, which may or may not be consumable, as we found in the case of the COVID use case? So let's fire that off as the first question. Yeah.
To me, Lavkesh, or to anybody?
Yes, to you, Ashwin.
Yeah, I mean, I think the key thing when you're building, I think there are problems where people are building machine learning models with experts or non-machine learning people in the loop. There's nothing wrong with the human in the loop being a machine learning person. But if that is not a machine learning able person, then I think there are many cases where this is happening. We just don't see enough talks maybe about real world use of machine learning, where there's a whole bunch of stuff that's happening after the whole data collection, cleaning. I mean, just as we don't hear much about the data collection, cleaning story, which is really as important or much more important than just the model building story. Similarly, I think there must be in the real world a lot of machine learning that does happen, where people are presenting models to non-technical users, which are then models are refined, data are refined, but whether the specific aspects being looked at by XAI and sort of saliency maps or relevance propagation, that sort of thing. I mean, those things do have a use, but they're really for machine learning people to understand why their models are doing what they're doing. I don't think they're intended seriously as a way in which say you would present to a doctor or a biologist or any other person like that as an explanation. But certainly, if that is being presented as an explanation to a biologist, it would be a pretty hard sell. There are problems where explanations are not needed, or at least in my case, the kind of case that I said, refutable explanations are not needed. But there are many problems in the real world where I think things like just giving the insides of a machine are not really the way to go. That much is certain. But I don't know whether the XAI community as a whole is working on that, but they're not really, it's not that they're not focusing on the right thing, but explanations have to be produced for a user. And if the user is a non-machine learning person, then they have to be produced in a different form. If the user is a machine learning person, then perhaps contrast maps are okay and things like that. So.
Right, but I mean, in most use cases, you will have an end user. If you're talking about deployable AI applications, you'll most likely have an end user that is not going to be a machine learning person, like a doctor or a finance professional or a IoT engineer, depending on what kind of application. So unless you kind of speak the same vocabulary as they do, you're right. It is not. It's just not going to work as a system.
Well,
So then
that's the key thing. I mean, this is all about deploying machine learning. It's not about the technique, just the tool. The machine learning component in it is one small piece in a bigger puzzle of using, using tools to understand things. And if that's the goal, then yes, I mean, there's a lot of stuff to be done, which people rarely talk about. But it's, I mean, you and I both know how much, for example, effort has to be done to get data into a reasonable form, but nobody really talks about that. So there are many aspects that people don't talk about, but doesn't mean that there aren't people who are not doing it. It's just that maybe we're not talking to the people who are doing it. So.
No, I'm purely talking about from what I'm reading and hearing at these top ML conferences.
Yes.
But
you've done a lot of real world deployment at TCS Research. Well, what has your experience been? I mean, can you get away with showing relevance maps and things like that?
Well, the demand for an explainable model has really just skyrocketed recently. It wasn't even a field till a little while ago. And so, but you're right, it's becoming increasingly difficult to deploy something, especially in critical areas. So we're moving machine learning from, kind of benign applications in advertising and online recommendations to critical applications in autonomous driving and medicine. And to do that, we do require to win the confidence of the end user. And to do that, we need to inject domain knowledge to be able to speak the same language. So, which brings me to my second question, which I want to direct to Indrajit, is given that modern AI, especially the deep learning world, there doesn't seem to be an established way of incorporating domain knowledge into these models, and that domain knowledge can come in so many diverse forms. How do we go about fixing this problem, not just for explainable AI, but for AI in general? How do we plug in the domain knowledge so that things are more understandable for the end user?
Yeah, thanks, Lokesh. So I was wondering, can I use a slide? So I had a picture which may make things a little more accessible. And okay, so let me try to share my screen and see if that happens. Okay, so is my screen visible?
Yes.
Okay, so let's try to move that around. So there's a lot that's happening around us in the world of machine learning, AI. That's relevant for today's conversation. And the question that you asked is sort of one of the two questions that I had thought of for discussion today. But before I went into that, so much of it will actually look like just a reiteration of what Ashwin talked about. But Ashwin, honestly, I did not make these slides while hearing you. I made them ahead of time. So so maybe I'll come to the second point first. So as you pointed out, Lokesh, the place where most of these knowledge-based symbolic machine learning AI gets stuck is this critical question. Where does this knowledge come from? If you're being a Bayesian, how do I set my prior? And we know at this point that there's no getting away from this by setting uninformative priors and stuff like that. It simply doesn't work. Right? So you're back to square zero. So where does this knowledge come from? So I've tried to indicate that with, I don't know if you can see the colors, they're probably too faint, but these green boxes that I have around are, potentially some answers to where this knowledge comes from, right? So there are these, Whitebox AI models that Ashwin was talking about, and each of them have their own way of doing knowledge discovery, if you will, right? Now, we understand that not all knowledge can come from data, right? And there are various forms of knowledge that simply cannot come from observational data, more specifically, right? And there, the work that's happening around causal discovery via experimentation and intervention is extremely important, right? That's one part of it, of going beyond observational data. The other, and again, this is what something along the lines of what Ashwin is suggesting, a lot of the knowledge still resides inside the heads of people, the experts, right? And these experts may not be the people who are actually, designing these machine learning models, right? They cannot directly encode this knowledge, right? And therein comes this other use of an AI that needs to be able to converse with humans or the user, I think, right? Because that's one very important source of knowledge, and the role of conversation to elicit knowledge from humans or experts is very important, I think. So again, going back to the example that Ashwin was saying, right? While the agent gave this explanation for a particular prediction, right? The user actually comes back saying, "Hey, but this does not agree with whatever I know, and maybe I didn't tell you this before," right? And so this human in the loop conversation is also important for building this domain knowledge. So I'll pause there.
Right, but the real issue that I think people get stuck on is, knowledge representation is part of the problem, and certainly identifying which is the correct knowledge representation, and for a particular use case, whether it's causal priors, whether it's system of differential equations, whether it's symbolic sort of rules that need to be enforced, is one thing, but actually combining all of these different sources into your machine learning model and plugging it in so that the predictions actually use this knowledge effectively and are able to pick out the correct pieces of knowledge for making a prediction is the second part of the problem, which at the moment I haven't seen it being solved. There are sort of some attempts at merging knowledge sources with deep networks and so on, but I haven't seen a comprehensive sort of solution to this. Would you agree, or do you think there is something?
Absolutely. We are. So so one sort of research thread that at least a small subsection of the AI community has been stressing on is this knowledge fusion problem, right? So Elias Barenboim and Judea Pearl have been talking about this problem for some time, right? And that's an unsolved problem, and probably it's very related to what you're talking about. So we understand that it's important, right? But I don't think we are anywhere close to that.
Right. It just seems to me that if we haven't solved that problem for making a prediction, it's going to be even harder to solve for generating an explanation for the prediction, or maybe not.
But maybe just baby steps are fine for the moment. Probably we should try and make explanations for individual types of knowledge to begin with, and then move on to the next step, because otherwise it's probably going to be, it's too hard a problem right now if you have not even solved it for any particular source or type of knowledge.
Agreed.
So, can
go
I
ahead,
interrupt
Ashwin.
here, Lavkesh? So here's a really crappy way to solve or answer your question, at least in, I mean, here's a really lousy way to do it, but suppose we just have a whole bunch of features and we don't know which of these are important. Now, it's not the case that there is a single subset of these features that is actually important for all kinds of aspects of this problem. So you can expect some subset of features to be important. Say, I mean, you take the simple case, for example, like if you're building a model that for which weighs, say, false positives to be more expensive than false negatives, then maybe your subset of features that you want to focus on is different to the subset that you would focus on if it was the other way, or if they were both equally. So the problem and the reason why it's hard, even when you know all the possible features that could possibly be relevant, is that it becomes a kind of subset selection type problem. That you say, well, for this subset, this is the subset that is important for this kind of use, for building this kind of model. So there's no one model. There's a sort of set of models, some of which use some subsets and some of which use some other subsets. So the problem, of course, becomes one of subset selection, which is intractable in its if you want to do it completely. But perhaps you could do some greedy thing for the kind of context or whatever that you want and find the subset that seems to at least give you some improvements in the loss or the decrease in the loss that you want. And that's all okay if you knew what sort of things you were finding subsets over, which is the sort of baby step version of one baby step version of what Indrajit said. The other more complicated thing is that I suppose there were just no, you had no idea what the starting representation was in the first place. And there, I think, of course, if you're dealing with somebody who was, well versed in the problem, then maybe you could say, well, that's not going to be really the case for that sort of person. He may know something about the problem. And then somebody would come back and say, well, then how do you go beyond what that guy knows? But then again, I would then go back to Indrajit's baby step problem. Let's at least go as far as that guy knows and then worry about going beyond him. So there are many versions of this baby steps thing which can be usefully incorporated. But I think the key thing is actually, if you really want to do this, you have to really be serious about closing this loop of building the model and refining things, in the sense that you want to be able to refine the representation or change the representation based on what came out as being useful. Or, I mean, presumably we're not interested in machines that produce useless models. But assuming that it's producing something useful, you want to see why it's doing that. But you have to be, I mean, doing that. I'm reminded of a line from, I don't know, some of you may not have seen this American series called Frasier, but in Frasier's brother was talking about dancing, and he said, this is boring yet difficult. And it's like that. I mean, it's closing this loop is boring yet difficult. I mean, it's not an easy thing to do. So,
which is probably why the deep learning community, which is so used to this pipeline of build model, generate results, and publish, probably is kind of washing its hands of this problem at
yes,
the moment.
But somebody takes the washed hand water and then does something with it after that. So I think there are people behind Pilot and they will do something about it, but we're not talking to them perhaps yet.
Well, that's some insight on the knowledge problem. I'd like to just talk, ask Tanuja a question about the other problem that I kind of foresee here is, the fact that we're not even utilizing all the theory, all the work that's been done in the behavioral sciences and human factors field for the design of an actual explanation. Given that the explanations have to finally be consumed by a human, it seems that that would be something we may want to look at. At the moment, I haven't seen anything like this, but do you have any insight into that?
Yeah, I think definitely it's an important problem, specifically looking at some of the class of problems that you talked about earlier, where the systems are getting deployed in the real world. And we are talking about AI-assisted systems, which means that AI systems are working in tandem with humans. And these users are eventually need to understand the results which are provided by AI systems. They need to consume those results. And also eventually, I think there are problems of accountability for eventually solving a particular problem or making a decision in real world systems, right? So there is a huge amount of work which has happened in understanding the human-computer interaction. Some parts of it have kind of started connecting with the explainability of AI, but definitely I feel that taking these different stakeholders who are going to be using these AI-assisted systems and what kind of information that they eventually need to make their decisions efficiently and effectively and take accountability of those decisions as well. It's important to have the whole HCI. In some sense, I think we need to marry HCI with the explainable AI systems and look at some of the work which has happened in HCI system, including participatory designs and thinking of this holistic picture of socio-technical systems rather than thinking of the ML systems in isolation from the users who would be eventually consuming the knowledge. And I think as we are moving with deploying the AI systems with more dangerous or in some sense as in more severe decisions, we are not going to go for a fully automated systems. And that's where it's very important that we make that interaction between humans and the AI systems more transparent, more easy to understand. And I think as Professor Ashwin said, as part of Two Axioms, is in how we understand machines and how machines understand the questions or the feedback which is provided by users, and putting that into kind of user interface which is useful for both users as well as machine is whole field which need to be explored. There is definitely a lot of interesting work which has started in this direction, but I think there is a lot that need to be still done looking at HCI plus explainable systems.
Well put, Tanuja. I think that's something I've always been concerned about. In fact, there's a paper out there that says, is explainable AI a case of the inmates running the asylum? So on that note, I'll move to the next question for Professor Shrikanta, which is, should we be even doing XAI? Is XAI, Cynthia Rudin, for example, thinks we should just throw away XAI altogether and just work on interpretable machine learning. And in general, there is something to think about here because, like I said, you're moving AI into critical domains and we've already seen that very well-trained AI systems, like I assume the Tesla self-driving system is fairly well-trained, it still crashes. And are we forcing through XAI, are we forcing trust into systems that are inherently kind of stochastic and unpredictable in some fashion? And should we be even doing this? So that's a question.
Thanks, Lokesh. I mean, this is actually something which even I have been thinking about for a while. And interestingly, let me just kind of cite a article that I saw recently in Scientific American. And it kind of took my breath away when the title of the article, "Oh, why airplanes are staying aloft," right? And this is 2020 we are talking about. And I thought, I studied Bernoulli's law. Of course, I knew why the airplane wings are like this, and I knew why airplane is flying. But apparently, it is not clear, even for experts, why really the airplane is flying, right? I mean, of course, basic principles are in place, but really, right? So given this vagueness about, I mean, this is more, I mean, you cannot find a more critical application than carrying a whole bunch of people 10,000 feet from the ground and hoping to help them. Despite the criticality of this problem, if you really wanted a scientific, accurate explanation of this, was impossible. Until apparently, even now, it is a big debate amongst people who are in this area. And we are talking about other critical applications where even the deep learning, or we don't even know why it is working the way it is working. And not just because of complexity of the model itself, but as I think Ashwin already pointed out, where did the training data come from? How biased or unbiased it was? Was it vetted by some people? Is there a way to go back and check what is the impact of one particular data point on the overall behavior? This is very clear, right? And we are talking about providing explanations to an end user, which I think is completely pointless exercise at this point, because even experts, machine learning experts, don't know why the model is working, right? Or often than not. So I think in some sense, I agree with, I think, Cynthia Rudin, when the point being debated is whether is it enough to provide sufficient information for an ML researcher in one particular, I mean, coming back to the airplane case, if airplane is not behaving properly, there is a engineer who can understand why a particular airplane is not stable, or should it be allowed to fly or not, right? If the expert can make sense or provide some way of trying to understand the model, right? That may be sufficient. I mean, end users don't need explainability. They need trust. They need a way of asking for recourse when something goes wrong, right? These are the two very important points. And dependability, of course, is a natural artifact when trustworthiness comes because of the explainability. That's, at least I'm taking a slightly counterpoint to some of my other colleagues here, but I really think we are overselling explainability being used by end users, because the moment we talk about end users, then we have to talk about their epistemic basis. I mean, what are they conversant? We explain it in the way they can understand or not. I mean, all of that is out in the open. I mean, we have no idea what this is. I think what we control are ML engineers, the guys who can actually, or the domain experts in case of Ashwin. I think even there I have some cribs about the way these answers could be misinterpreted. For example, I don't know if radiologists would say a model's explanation is bad whenever they disagree with on the other hand, when they agree with it, they find the explanation, of course, it perfectly fits my worldview, right? Is this the correct explanation? I don't know, right? So there are many complexities, and I think we should stick to something as scientists we have control on, which is interpretable and machine learning system. And I think that's what I would like to end my little argument here, but let's see.
And there's also a flip side to that whole argument, and I think you touched upon it there, which is what if the AI system is actually much better at the assigned task than humans are? And we may not understand how it's doing it, but it is just better. So let's assume for a moment that self-driving cars are actually much safer than human-driven cars, and we don't understand how they work completely, but they're just safer. Now, is it ethical to use them or to not use them, actually? That's another sort of...
I mean, people have been using automated character recognition for sorting sorting mail, and we have no idea why it works, and we have been using it, right? I mean, at least now we probably know more, but I think when it was deployed, probably in US Postal Service, people didn't really know about it, but they were happy to use it because it was working.
Well, I'm afraid we'll have to take we'll have to end it here and take some questions from the audience.
Sure.
So Gunja asks, it's been said that domain knowledge will help us understand the data in a better way, but how do we segregate the domain knowledge into good or bad knowledge? I think she's talking about the knowledge retrieval part of the story. Ashwin, you want to take that one?
Well, I didn't say that domain knowledge will help us understand better. I said that it helps the machine understand better. So it's the machine's job to decide which is good and bad as such. If it can't work out what is good and bad in what domain knowledge is provided, then it doesn't help it understand better, at least in the position that I'm taking. So if I give it a whole bunch of very clever constraints and it doesn't have a constraint solver, then it's just gibberish for it. So it's got nothing it can do. So so that's sort of sidestepping the question by saying that, well, that's not really an answer, is it? I mean, you're not telling me how the machine should do it. Well, I can tell you how the machine should do it for the kinds of problems that I look at in the kind of machine learning that I do, but I don't know how that should do it in, say, in some other kinds of machine learning. But it's known how to decide what is relevant and what is not relevant. I mean, you have to have a notion of relevance, yeah? So you cannot just say, how do we know what is relevant and irrelevant if you don't know what the word relevant or irrelevant means as such for a machine. So a machine has to have a notion of relevance, first of all, and then it has to be able to decide relevance based on that. But certainly I wasn't proposing that domain knowledge makes us understand better. So it's to help the machine do slightly better.
Right. Sumit asks, I wonder if one extension of the idea of being able to refute machine explanations might be the ability to interrogate machines as a means of gauging understanding. Turing, in his 1950 paper, Turing test, mentions how this would be similar to the way to judge the understanding of humans via a Viva exam, for example.
Yeah, so Turing's paper is sort of very much like an Oxford Dons paper on, so he probably had an Oxford interview in mind when he was answering, or a Cambridge one anyway. But yeah, I mean, I think the refutation to be able to, I mean, this is so far ahead of what we're doing at the moment. I think about, say, for example, being able to converse with machines and provide, counter question, which can then be answered in some way. I mean, some aspects of that we know For example, if a machine says that this is why I think this this example is or this instance is such and such, and you say, oh well, what do you think of this other thing then? And it comes back with some statement saying, oh yes, well I think this is something else because of this sort of thing. So you can do that kind of conversation. But yes, it would be a good thing to do. I think in a sort of legal, if we want to have any kind of legal trust, I don't know whether we'll have human style trust, but legal style trust, then we certainly must be able to interrogate these machines in the sense that it's not just about the fact that you think that this guy. I mean, for example, I mean, let us make it slightly more interesting and say, well, so you know, if you really want to discover whether the machine learning model has some kind of racial bias or something like that, because based on the kind of prediction that it made you suspect you didn't agree with the explanation, so you were able to refute it. So that's as far as I was going in my talk. I just said that if you're able to refute it, you at least understood what it was saying. But if you really want to understand the model itself, and you wanted to discover, for example, that actually this lousy machine is actually, you know, deeply racially biased, and that's why it's making these predictions, then you may want to say, well, what about, you know, what about if this was, you know, a white Anglo-Saxon male, and, you know, getting out of a BMW, would you say the same thing? And then you say, oh no, it won't, and so on, you know. So you'd certainly want the ability to do that eventually. But that's to try and understand the full model. I was only talking about understanding the explanation that it gave. So
I think it's, Ashwin, just to add, it's a little more than just understanding the model. It's actually understanding the data on which the model was trained and how it was collected, how it was processed, how it was consumed. I think you already mentioned it some time ago, but I just wanted to re-highlight
yeah, it's, I mean,
that point. Yeah.
there's a long way to go in all of this. I mean, it's just being able to take a file of data and producing a set of predictions is nowhere near what we really want to do with in the big machine learning picture anyway. So
I think we have time for just one final question. This is from Gautam. He asks that, you know, if model interpretability can point a user to similar training data and the ground truth therein, maybe there is a sufficient explanation for some scenarios. I'm going to let Shrikanta take this one since he's the one least convinced by XAI. So could it be a sufficient explanation for some scenarios if you fetched some, some patients, for example, similar with the similar sort of diagnosis and outcomes and features, and said that, you know, this is why I'm diagnosing this patient with a disease because all these other patients that look like him had this disease. Would that convince you or no?
See, that would probably convince in some limited scenarios. I mean, in this particular case, yes, maybe. And I'm able to make that the examples that you have given of similar patients is similar enough in my view, right? I mean, of course, doctors disagree that no two patients are the same, but we are looking at some features that we believe are common between these patients, right? But I don't think it is true in sense. This particular approach of trying to convince me whether this model is correct or wrong, because it also depends on what do I know about. I mean, again, I have a fundamental question with this notion of domain expertise itself. But I mean, who is a domain expert? Can I call a, let's say, general health center same expertise as somebody, a serious brain surgeon, right? I mean, both are domain experts, both have doctor degree. I mean, they can call themselves doctors, but it's a little more complex than just saying domain expert, and they can identify similar patients. I think it's not, it may work in some cases, but not in general, right? We need to have a common model of who is consuming your, whatever you're presenting, either as an interpretable interpretation of the model or the explanation of the model. You need to also have a model of the consumer.
All right, I think our time's up. So thank you, panel, for this great discussion. Special thanks to Ashwin, who's, I think it's well past midnight where he is. So thank you for doing this.